So today's lesson, I explain about the circuits of protection. So the circuit protection, when the electrical fault happen, so the circuit device are automatically disconnected. So automation, disconnection of supply. In this case, we are using the classroom equipment to do the electrical separation. So classroom the ASR3000 standard, we had to follow the clause of 2x4x2 protection by automatic disconnection of supply, and 2x4x3 is a diode devices. So it includes the enclosed fuse link ASR60269, miniatures overcurrents breaker, crossing the ASR3111, and mode case circuit breaker ASR60947.2, and fixed setting of the RCD ASR3190. Also, the semi-enclosed rewirable fuse that shall not be used. This is for the kind of the equipment used for the circuit protection. So when there's a protection against the circuit, this is the normal. The blue color is a normal electrical wave, but the red color is a fault current wave. So when the fault current is higher, it happens. So we have to protect the fault. We cannot allow the fault current to reach a maximum point. So when the fault current reaches a peak point, the equipment has already been blown out. So that we have to protect the circuit breaker should disconnect the supply when the fault current will reach to the 25% of the supply. So this is the ways fuse and circuit breakers are designed to operate. Fuse and circuit breaker operate to cut off the supply. In this case, we also have to allocate the protection coordination. 2x5 and 3x1 is a protection coordination. IB is the maximum demand of the current. So across the AS3000, we use the appendix C1. IA is the nominal current of protected device. 10 ampere to utilize. IZ is the continuous current capacity of the conductor. AS3000A utilized. So the customer protection configuration IB less than IM less than IZ. So that also the I2 is less than or equal 1/4 times IZ. I2 is the effective operation current. So it need to follow the above equation to coordinate the protection. Therefore, this will be the maximum demand current is less than the equal the nominal current protected current, and also the continuous current carrying capacity of the circuit. So this equation must be followed to do the protection coordination. So that across the cross 2x4x1 protection against the short circuit current, the prospective short circuit current at the current carrying capacity, the prospective short circuit current at the every relevant point of the electrical installation shall be determined by the calculation. So this calculation T equal to K square S square by I square. This equation utilized to calculate the protection short circuit current. So that in this case, the T is a short circuit current time of the duration, K is a material factor, A is a conductor cross in the area, and I is a very short circuit current. So this is as overload the short circuit protection. Devices are constructed. So in this protection device, we must follow the ASR2x5x2. Overload current is a device and also overload short circuit protection devices. So those are the have to arrange. So the overload short circuit current must be followed the AS3000 standard 2x5 and 3x2 and 2x5 by 4x2. So the 2x5x2 machine about the circuit breaker. This is the overload and the short circuits are released. Fuse coordination units are also included. HRC fuse also included. Circuit breaker in conjunction with the fuse. AS2x5 and 3x2 is a possession of the protection devices. 2x5 by 4x2 is a possession of short circuit devices. Those standard rules must be followed. So in this case, our protection circuit, this is a consumer here. This we have to allocate the base rate. Here we locate the sum base rate. So this is a typical installation of circuit arrangement. Supply here, consumer service view, kilowatt hour meter. This is for the water heater. We supply the water heater, kilowatt hour meter base rate, and we connect it to the light and the power. Also, we connect the RCD protected devices And this neutral is a RCD protected neutral. So this is a protected neutral. And here connected to a neutral link. Everyone go to the subline go to neutral link. So then here connected to a subline neutral link and connected to the R. So this is the ambient link. This is the configuration of the electrical power supply system for the typical building. So there will be this circuit. You see the water heater circuit, main switch, and RCD protection for the light and the power switch, direct connection to the light, range, and the power, and also the protected neutral link, unprotected neutral, and also supply neutral link and the unlink. So this is for the typical wiring arrangement. Then you have to do those tutorial. Those are the answer for the tutorial. Then we're talking about the alpha protection. A leaking current cannot be protected by the circuit breaker and fuse. This system needs to be provided to the metallic body of the equipment. RCD are the residual current devices for the unleakage protection. So RCD classification in the type 1 is a residual current, nodes are exceeding the 10 milliampere. Type 2 residual current between 10 milliampere and 30 milliampere. Type 3 is a residual current between 30 milliampere and 300 milliampere. Type 4 is a type 3 with selected tripping currents are time delay. So those are the RCD classification. Also the portable RCDs are the class A is a household. So this is a general use. Class A is a general industrial use. So we have to follow the AS/NS 3190 and 3003. And also the selection of the arrangement. The load current rating of the RCD shall not be less than the greater of the following: the maximum demand of the position of the electrical installation being protected by the device, and the highest rating of the any overloads are protected devices. Here is a type of the RCD. So this is the AC RCD. So AC RCD with residual oscillating DC. Here is a this is as for the type A and residual sinusoidal and residual the DC. And here is a time delay with the S symbol. So this is for the type of the RCD. So here is a typical supply arrangement for the RCD and the main switch. Supply switch at neutral link. And here we give with the physical diagram. This is a circuit connection diagram. So this circuit connection diagram of the supply. And this is for the physical arrangement of the switch. And then this is we do this on the tutorial. Then the next one is the follow impedance. The follow impedance is this is a resistance ring, and here with the 60 ampere fuse, and this is low, and this is the resistance of the arting. So RE is a less 2 ohm, and for resistance of the low is a 2 ohm like this. Resistance of the return R2 is a 12 ohm. So there will be this supply here, the active wire line, the fuse low, and this is return line, the for resistance. So the total resistance is R line plus R low plus RE plus RCL. So this is all the resistance have in from the R low, the current flow here, go to low and return to the low. So all resistance have to be added. The resistance value are already given in the value. Line resistance is 0.2 ohm, and R4 resistance is a 2 ohm. Adding conductor resistance is 2 ohm. Neutral resistance also given. So add everything. You got the R total you got. And supply voltage 240 volt 204 divided by the resistance total. You got the current of 45 ampere. You need to know the adding to impedance to calculate the R4 current. So this slide shows the connection of the switch, and also this is the conductor switch, and this is for the conduit wiring. This is for the length of the cross-sectional area of conductor. If you know the length of the area, RCD and RE, RCD the impedance of the active conductor, CDP and figure, and this is for the RE is the impedance protected active conductor. So this is the external, and this is internal active conductor resistance. And in this case, Z is 0.8 multiplied by U 0 divided by the HA. So this equation. So this is how to calculate internal impedance calculation. This one shows the maximum value of the output impedance depending on the protected device rating. the circuit breaker type B, C, D, and fuse. And this is for the maximum output impedance. This one you can see it. This is for the protected by rating and maximum output impedance relationship. And this program find the circuit output impedance calculation. So if find the circuits are supplying the load consisting of a range in the domestic installation and is protected by the 22 ampere type C circuit breaker, determine the maximum internal for loop impedance of the final circuit based on the 230 volt when the supply is unusable. So in this case, the system for loop impedance we should use a table 8.1. So in this case, table 8.1 is a we have find out this upper loop impedance, and also the cross 5.2 is a internal impedance 0.89 ZS. So the front table 8.1 32 ampere type C circuit breaker this is a 0.96 ohm. So here 32 ampere 0.0 is a 0.96 ohm. This is the type C circuit breaker 32 ampere 0.96 ohm. This 0.96 ohm is a you substitute in this equation. Then multiply with 0.8. So ZIND is a 0.89 ZS. So the 0.8 multiply 0.96, you got a 0.768 ohm. The next one is the final circuit. The final circuits are final circuit supply is the load consisting of the 15 ampere socket outlet and protected by the 25 ampere HRC fuse. Determine the maximum internal for loop impedance of the final circuit based on the 230 volt when the supply are available. So the operating time of the HRC fuse is 0.4 seconds. So this is the high brush charging capacity. Table 8.1 is a 25 ampere HRC fuse. So that will be the 0.4 seconds. So you is operated that is equal to 1.64 ohm. So that we also have to use the appendix B plus 5.2/4. ZIND the 0.8 ZS to the 0.8 multiply 0.64, you got a 1.312 ohm. And we also follow the finance for current is the current from the active to switch and then go to the link, neutral link, and go to the neutral. So the next problems are finding circuit supply the load position of the process and luminance, and is protected by the 10 ampere type C circuit breaker. We determine the maximum internal for loop impedance of the final circuit based on the 230 volt when the supply are available. So in this case, type C circuit breaker ZA is 2.307 ohm, and so 0.8 minus ZS go 0.8 minus 3.07, you got a 2.46 ohm. Then we also have to calculate the calculation of the fault current. Percentage impedance is a fault load current, full load current multiplied impedance by the phase voltage by 200. So the percentage is the IF HV by EJ into 100. So the full load current can be calculated full load KVA multiplied 10^3 divided by 2/3 to line voltage. So that equation you will. So in this case, a big problem. Consumer main is a 0.0007 ohm. Next week, and supply is a 0.2 ohm per phase. So 500 volts, 3 phase are supply utilized, primary 22 kilovolts, secondary 415 volt. We have to find a fault current. So HTA is going to be determined 0.2 minus 0.02 minus 0.0007. You got a 0.0207 ohm. IF is a KVA by 10^3 divided by 2/3 ES. So 500 into 10^3 divided by 1.732 multiplied by 415. You got a 695 ampere. Then we find out the percentage is IF at HCV and EBA into 100. So the IF at 645, HBA 0.0207 divided by 415.23 divided by 2 multiplied by 100. So you got a 5.94 ohm. So ISA equal to IF at percentage is 100. So 695 divided by 5.94 into 100. You got a 11602 ohm ampere. Then we also got a master connection. Meter connections are diagrammed in accordance with the New South Wales electrical service rule. When you are using the meter, we need to follow the New South Wales electrical service rule. So the New South Wales electrical service rule you can follow from the Google, and so google.com type an electrical service rule. And then you can see the section 4. In this case, a circuit metering equipment. Section 4, page 15 is wiring diagram for the bottom connected metering. You can see all the NSU electrical service rule. So this is the typical connection of the meter connection, gateway meter 1, gateway 2, gateway 3. So this is hot water, lighting, and the power. And these are C's at the neutral, distributor neutral, connected to consumer neutral link. Here we connected to the consumers set. Controls our protection devices. So this is what the meters are arrangement diagram. So this is a typical fuse and the metering arrangement diagram inside in the New South Wales electrical service group. So this is for the cloud connection diagram, and this is the physical connection diagram. Those are fuse, those are the RCD, and those are early neutral link. So those are the diagrams. So this one is show the connections are arrangement diagram, and this is a physical connection diagram. So this is at the back connection like this. The connection diagram of the metering devices. Then you have to do the tutorial. We have to design a masonry board, install a 3 kWh meter for the hot water, lighting, and the power by applying the New South Wales electrical survey rule, survey and metering equipment installation. So those are the circuit diagram here. This is a circuit diagram. This is a physical connection diagram. So this one today lesson I explain you about the processing devices and use all the New South Wales electrical service rule, and also the protection device arrangement. In the meantime, we also have to do the electrical trade too. Then we go to the electrical trade 2022.htm. Then we do the last week I told you about to read the G103. Now you have to read the G106. Wobble. So go to this side. I joined the college.com/electrical trade 2022.htm. This link here. I joined the college.com/electrical trade 2022.htm. So this one's firstly go to the electrical trade 2022.htm. So this is the I joined the college.com/IQI technical college.com/electrical trade 2022.htm. So when you enter through the electrical trade 2022.htm, you see the display page. So those are the unit. So this unit and the EI is a mapping. So this is for the UE11 course. For the UE20 board, there is a mapping. So my lesson based on the UE11, but if you are doing the UE20, this is the mapping table. So this is the mapping table. Electrotechnology electrician. For the last week we talked about the UE and the GSA 103. And 103 and 104, that combination is equivalent to the UEES 0012. So this is for the combination equivalent unit. Now we're talking about the UE and the G106. UE and the G106 terminate given cost and associated for low voltage circuit. This is equivalent to the UEES 0023. Terminate given cost and associated low voltage circuit. So this is for the UE 3011. This is the UE 30820. So this is the relationship between the O and the new unit. Therefore, the by using this book, QE, G1 will say this is also got the equivalence unit and then use codes. So that these codes we click this one. Here is workbook. You read through the workbook. Workbook is a lesson. You also read the workbook, and here is the workbook answer. The answer you read as an answer for the workbook. This is the answer for the workbook, and also the video. All the competency in the workbooks are video. You can see the practical video. So you have to view those videos. So this is today is you have to do the G1 set. The G1 set you have to do those things. Then we're talking about the Bachelor of Applied Engineering Electrical. We talk about the AC circuit. Last week we have already explained you about the AC circuit principle. G1 2. So the G1 2 AC1 circuit. I continue the AC circuit. So last week we had explained about the G1 2 section 1 and 2. Now we're talking about the section 3 and 4. Series RS circuit. Now we're talking about the G1 202A. B. Resistive AC circuit. So this is for the solder problem in low voltage AC circuit, resistive AC circuit. So at the end of this session, students should be able to apply their own laws in resistive AC circuit, state the phase relationship between voltage and current in a resistive AC circuit, draw the phasor diagram for a resistive AC circuit, calculate the power consumed by a resistive AC circuit. So that this is for the impedance equation that is equal to V divided by I. This is own law for the AC circuit. Impedance Z is a 3 component. That will be a resistance. This is for the horizontal line resistance. Inductance is a H particle line, and this is the HA is an inductive reactance, H is a capacitive reactance, Z is an impedance. This angle theta is the angle between voltage and current. So this is the component of the resistive AC circuit. So that this is called the impedance triangle. Then we're going to talking about the power triangle. So this is the power triangle, the angle between voltage and current. This power is apparent power S. This is voltage minus current. So VI cos theta is a real power. P equal to VI cos theta real power. The cos theta is called the power factor of the circuit because it related to the real power to apparent power. So this one is apparent power. And here is the vertical is a Q. Q is a VI sin theta or reactive power Q. So in this case, this is a circuit here. This is resistive VT current flowing, ID current flowing. In a purely resistive circuit, the current is in phase with the voltage. So resistive current is in phase with the voltage. In this case, the vector diagram, current and voltage diagram, you can draw like this. So the for the power triangles are S equal to VI, P equal to VI cos theta, Q VI sin theta. P equal to VI, in this case, Q equal to 0 for the pure resistive circuit. So in this case, the voltage and currents are in phase. Voltage is purple, you can see current here, they are in phase. This is for the pure resistance circuit. Power will be there, the black one is a power is ever positive. So resistance is a property of circuit. This that opposite current flow. In any circuit, Z equal to V divided by I. So that in purely resistor circuit, Z is equal to the R. So that in the AC circuit, the voltage continually changing, but the resistance is constant. So in this case, resistance and the voltage are the purely. So in this case, a phase angle is a 0 because Z and I are the same. Then we doing about the example calculation. In this case, you have to know the formula V equal to Z equal to V by I, S equal to V into I, P equal to VI cos theta, Q equal to VI sin theta, Z equal to the R. Example 1, that the element of the toaster has a resistance of 60 ohm determine the circuit current if the toaster is connected to the 240 volt 50 Hz supply. What do we know? In this case, I equal to 60 ohm and V equal to 240 volt. What do we want to know? I equal to V divided by Z. So the 240 by 60, you got a 4 ampere. A purely resistance that is connected to the 24 volt 50 Hz supply. It will then draws at 1.25 ampere determine a circuit resistance, circuit impedance power consumption. So what do we know? In this case, our voltage 24 volt, current 1.25 ampere. What do we want to know? We want to know that Z equal to R, Z equal to V by I, and then power equal to VI cos theta. So in this case, Z value you find out 24 by 1.25, Z got 90.2 ohm, and power equal to 24 by 1.25 multiplied by 1, you got the 31. This is the we got. The next problem is 2K2 ohms resistor is connected to the sine generator. If the frequency of the signal is set to be the 2 kHz and the circuit draw the 4 microampere, determine the output voltage of the generator. What do we know? So we know that Z equal to I equal to 2K2 also, and also the frequency 2 kHz, current 4 microampere. What do we want to know? We have to know that V equal to IZ, we equal to 2200 multiplied by 4 microampere, so the 8.8 millivolt we got. The circuit has a resistance of the 20 ohm and the draw the current of the 16 ampere. Determine the applied voltage, circuit impedance, and the power drawn by the circuit. What do we know? We know that resistance 20 ohm, current is 16 ampere. What do we want to know? In this case, voltage equal to Z multiply ZI. So in this case, V equal to R, P equal to VI. So in this case, Z equal to I equal to 20 ohm, P equal to, so voltage equal to ZI, so 20 multiplied 16, you got the 320 volt. Power equal to V into I, so 320 multiplied 16, you got the 5.12 kilowatt. Then this is for the answer. We finish. The next one will be the resistance capacitive AC circuit. So UENEG 102A saw the program in the low voltage AC circuit. We know about the capacitive AC circuit. At the end of this lesson, students should be able to list the effects and the application of capacitor in AC circuit, define the terms of capacitive reactance, draw the impedance current and voltage phasor in the ID capacitive circuit, calculate the impedance current and voltage in an ID capacitive circuit given certain characteristics, and calculate the impedance power consumed by the capacitive AC circuit. So this is for the capacitive AC circuit. Capacitor C connected voltage VT. Capacitor is a property of circuit that opposes the change in voltage. In a pure capacitive AC circuit, the current leads the voltage by 90 degrees. So this is the current leads the voltage by 90 degrees. And in this case, the power triangle V equal to S equal to VI, T equal to theta, and the P equal to VI cos theta, Q and VI sin theta. In pure capacitive circuit, the lead the voltage theta is 90 degrees. So this is the voltage here, the current here. Voltage lead the current by current lead the voltage by 90 degrees. So this is the power. Well, this is Q. The reactive power Q equal to VI. Real power is 0. And capacity is a property of circuit that opposes the change in voltage. So the any circuit Z equal to V by I. Z is equivalent to the AC. So the AC equal to 1 by 2 by SC. In this case, S is the frequency, C is the capacitance value. So this is AC value, this is Z value, this is R value. And Heisenberg calculations are CIVIL. So the equation. So in this case, Z equal to V by I, S equal to VI, P equal to VI cos theta, Q equal to VI sin theta. Z equal to approximate to the AC. So AC equal to 1 by 2 by SC, H equal to 2 by L. Determine the impedance of Puma capacitive circuit which draw the 4x7 ampere from the 240 volt 50 Hz supply. What do we know? I equal to 4x7 ampere, we get to 240 volt. What do we want to know? Z, we need to find out. In this case, Z equal to AC, so AC equal to V by I. AC equal to 240 by 4 by 7, you got the 51 ohm. Determine the reactant and the circuit currents are drawn by an 8 microfarad capacitor connected to a 240 volt 50 Hz supply. Draw the phasor diagram for the component. What do we know? So C equal to 8 microfarad, V equal to 40 volt, F equal to 50 Hz. What do we want to know? AC equal to 1 by 2 by SC, I equal to V by Z. So CIVIL, so we calculate. So in this case, the phasor diagram is drawn in a different scale. So the AC equal to 1 by 2 by S0, 1 by 2 F, 2 by minus 50 into 8 microfarad, I equal to V by Z. So AC value is 397, Y is 890, I equal to V by Z, 240 by 397, Y89, we can calculate the current is 0.603 ampere. So current is 0.6 ampere. Single phase synchronous motor draw the 40 ampere with the leading power factor of the 0.22. Draw is a 240 volt. So 50 Hz supply, determine the rated and true power. So what do we know? Currents are 40 ampere and also power factor angle, power factor is 0.22 leading, and voltage is 240 volt, frequency 50 Hz. What do we want to know? In this case, appearance are power target, apparent power, this is real power, reactive power, this is angle, S equal to V into I. 240 multiplied by 40, you got then 9.6 kVA. P equal to VI cos theta. Cos theta is a value is given, so the power equal to 9.6 multiplied by 0.22, you got the 2.1 kilowatt. Calculate the phase angle for the circuit which has a power factor of the 0.1 leading and a 0.33 leading. So in this case, what do we know? Power factor angle values are given, the 0.1 leading and 0.33 leading. Circuits are capacitive, apparent power, the reactive power and real power. So what do we want to know? Theta A is you have to find the cos value, cos in 0.1, so you got the 84.26 degree. Theta B is a cos in 0.33, you got the 70.73 degree. And this is for the phase angle. Phase angle for circuit, power factor 0.1 leading and 0.3 leading. So there will be the power factor 0.1 and 0.3 leading, we can calculate by this way. Capacitance of the calculate the capacitance of capacitor if the capacity reactant 100 ohm at the frequency 50 Hz. So then what do we know? H equal to 100 ohm, F is 50 Hz. What do we want to know? Capacitance we have to find. So H equal to 1 by 2 by SC, so C equal to 1 by 2 by FXC. So 1 by 2 by 100 pi into 100, you got the 31.8 microfarad. Determine the current taken by the 100 microfarad capacitor which is connected to a 230 volt 50 Hz supply. What do we know is the capacitor is 100 microfarad, voltage is 230 volt, frequency 50 Hz. What do we want to know? We have to find the current. So H equal to 1 by 2 by SC, 1 by 100 pi into 100 mu, you got the 31.8 ohm, V I equal to V by itself, 230 by 31.8, 7.23 ampere. Then you have to do the practical exercise. Then we also talk about another inductive AC circuit. Inductive AC circuit, we talk about. So the sort of problem in low voltage AC circuit. Inductive AC circuit. So at the end of this lesson, students should be able to list the effects and application of inductance in AC circuit, define the time inductors are reactant, draw the impedance circuit, impedance current and voltage phasor in the ID inductive circuit, calculate the impedance current and voltage in the ID inductive circuit given certain characteristic, calculate the power consumed by the inductive AC circuit. So this is for the inductor connection. Is the inductor current flowing. Inductor is the properties of the circuit that oppose the chain current. The pure inductive circuit current less the body by 90 degree. So this is current less the body by 90 degree. We are inductive circuit. And it's also the power triangle. P equal to VI cos theta. S the VI, Q is the VI sine theta. Pure inductive circuit. Let the Q is a minus 90 degree, cos minus 90 is 0, sine minus 90 is minus 1. So this is voltage and the current we got. And here is a phasor diagram. This is the Q. P is 0, Q equal to minus VI. Practical inductor has a same resistance and therefore the use a some real power I square R. Inductor are used in the AC circuit because they use a very little real power. Inductance is a property of a circuit that opposes a change in current. So any circuit Z equal to V by I. So that in this case Z is approximately to the HL as an inductive reactance. In an AC circuit, all the voltage continually changing, and the inductive reactance is a frequency independent. So HL equal to 2 by FL. Phase angle is a theta 90 degree. This is HL value. Then we have to calculate Z equal to V by I, S equal to VI, P equal to VI cos theta, Q equal to VI sin theta. So Z is approximately to the HL. Magnitude of HL is 2 by FL. So determine the impedance of the inductor if it draws the 1 by 8 ampere from the 230 volt 50 hertz supply. So what do we know is that I is to 1 by 8 ampere, V 240 volt. What do we want to know Z? We have to determine Z equal to HS approximately equal to the voltage by I current. So in this case, Z equal to HS to V by I, 240 by 1 by 8, you got that 133.30. The next problem, determine the impedance and the inductance of the coil with the negligible resistance, which draw the 0.2 ampere when connected to a 240 volt 50 hertz supply. Draw the phasor diagram for this component. What do we know? We know the current I is a 0.2 ampere, voltage 240 volt, frequency 50 hertz. What do we want to know? Impedance Z. In this case, Z equal to HL equal to V by I. HL equal to 240 by 0.2, you got a 1200 ohm. HL equal to 2 by FL, then you have to find out the L equal to HL by 2 by F. 1200 divided by 2 by 50, you got the 3 by 8200. Then you got the diagram, the body. Here, this is current. So this is a phasor drawing diagram. Draw the VI power phasor diagram with the value for the 0.2 Henry coil with a negligible resistance when it is connected to the 240 volt 50 hertz supply. What do we know? A is equal to 0.2 Henry, B equal to 240 volt, F is 50 hertz. What do we want to know? CI, VIL. So in this case, this will be the phasor are the drawing different scale, voltage 240 volt. So I equal to V by Z. So in this case, H equal to 2 by into 50 into 0.2, you got the 62 by 80. I equal to 240 by 62 by 8, so 3 by 82 ampere we got. The next problem is draw the 40 ampere with the lagging power factor of 0.22 from the 240 volt 50 hertz supply. Determine the apparent and the true power for the weather. So what do we know is that I equal to 40 ampere. In this case, angle is at 0.22, leading voltage 240 volt, frequency 50 hertz. What do we want to know? So this is real power triangle. This is theta apparent power. This is reactive power. So S equal to VI you got. S equal to 240 into 40 and 9.6 kVA. P equal to VI cos theta. So angle is at cos theta. P equal to 9.6 kilo ohm multiplied by 0.22, you got a 2.1 kilowatt. Calculate the phase angle for the circuit. Power factor is a 0.76 lagging and 0.96 lagging. What do we know? So the angle is a 0.76 lagging and 0.96 lagging. The circuits are inductive. Real power, reactive power, apparent power here. What do we want to know is a theta is cos about 0.76, you got the minus 40.5 degree. Theta is a cos about 0.96, you got the minus 65 degree. The next problem is ID inductors are draw the 10 ampere from the 240 volt 50 hertz supply. How much current would it draw from the 120 volt 100 hertz supply? What do we know is that I1 is 10 ampere, V1 240 volt, F1 is a 50 hertz. What do we want to know? I2 is to determine V2 120 volt, F2 100 hertz. So that in this case, I equal to V by Z. Z equal to H equal to 2 by F. HL1 is V by I equal to 240 by 10, so you got 24 ohm. So L equal to HL1 divided by 2 by S, so 24 by 2 by into 50, you got a 76.4 millihenry. HL2 is 2 by F, so 2 by into 100, you got a 76.4 millihenry. Then you got a 48 ohm. Then frequency F is a 2F1, so the HL2 is 2HL1, so you got a 248 ohm. Then here you call the I2 is 120/48, so I2 2.5 ampere. Okay, this is for the advanced diploma electrical. So then we also do the advanced diploma electrical.
Oh, this is a DISSEN.
So now we continue to do the advanced diploma electrical engineering. So the website is here. I give you the website. The website is IQI-college.com/electrical diploma 2022.htm. IQI-college.com/electrical diploma 2022.htm. So you click to the this side and we enter. Here is a mapping between the UE 62211 and UE 62220. So this is the mapping between the old and the new unit. So my lesson based on the old unit, but for the new diploma course, you can map to the new unit. Study option 3 is a YouTube video for electrical engineering lesson. So you have to find out the Go and YouTube video for electrical engineering lesson. Then you click the lesson. So last week we have already explained you about the to study the project unit G069 project unit. I explain you. Now today's G012 I already talked. And you have to do this power system protection. IS67. IS67 electrical power system. IS74 power system protection. So the those lesson notes are here. You click the highlightcomputer.com/video lesson.pdf. So the page 196-231. Those are the written lesson for the video. Videos are here. Those video you view the video. Those are video you have to view the video. Those are the videos electrical distribution, demand factor set like this. So those are the components of the electrical video. Those video you have to view and you have to read the note here. So this is the ways how you can study the power system protection, electrical power system 1.